Okay, so we can start. Welcome everyone to the Thursday seminar. Today we have Vasco from Belgium, from Leuven, whom you actually heard on Zoom 2 years ago, but now he's with us in real life. So he will talk about five-dimensional black holes.
Yes, so hi, thanks for having me here. And it's actually convenient for me that the talk is in English because last time there were some words that I could not translate properly. Anyway, so I will be talking about the goal.
But maybe sometimes you should learn Bulgarian.
I know Bulgarian, but just the physics in
No, I mean the physics.
Yeah, the physics in Bulgarian is.
Of course, if you never give another talk.
Yes, well, we can try to give another Bulgarian version of this. Okay, so what I'm going to be talking about is a test of the ADS-CFT duality. So what is the ADS-CFT duality? It's a statement that quantum field theory in certain number of dimensions is equivalent to quantum gravity theory in more dimensions. So in particular, I will focus on an ADS-5 CFT4 example, and practically the duality states that the partition functions of, in this case, I will focus on an example of ADS-CFT coming from M theory. So the statement is that the partition function of M theory and I will explain the notation. Is equivalent to the, and this is on ADS-5 times an internal manifold which is compact. And just tell me if I need to write larger or more legible. Is equivalent to the partition function of the conformal field theory on R cross S3. So this means that there's a number of fugacities here. So basically some thermodynamic setup that we fix to calculate this partition function. And these fugacities can be read as the boundary values of some bulk fields as they approach the boundary of this ADS space. So this is the full-fledged version of the statement, and of course it's very hard to prove this statement because, well, both of these objects on the left hand side and on the right hand side are generically hard to compute. So
Is the left hand side even well defined?
yeah, so that's even another question: is the left hand side defined? So because we're doing, I'm taking an example from M theory. There is the microscopic description of M theory is not known. The only thing that is known is the low energy approximation, which is the beloved 11D supergravity. But that's just the low energy limit of the full M theory. So to make progress on this duality, then there is one parameter that controls the whole story, and this is n. I will give a precise description of what n is, but for now it's just a number that comes from the n theory description of this statement. And as this number is large, we can make progress, because when the number is large, this theory, we can study it in the supergravity approximation, and we can calculate the leading behavior in large n. Unfortunately, on the other side of the duality, the physics is strongly coupled. And being strongly coupled generically is very hard to compute anything, but there are certain tricks, and I'm going to explain one of them, in which, again, in the large n limit, one can calculate this object. and compare if they match. Now, this duality has been extensively tested in the to leading order in large N. So, for example, like this object here, in our particular case, would go like something like this. It will be n cubed. You'll see why it's n cubed in particular. It will scale as n cubed. And this object also scales as n cubed. And by a test of the duality, we mean that this coefficient and this coefficient are the same. However, we can do better on this side of the duality. There are ways to compute the next term in an expansion in large N. And there is a prediction of what gravity should be able to reproduce both this coefficient and this coefficient. And in many tests of the duality, what has been achieved is compute the leading term, and I will show you the results from recent work that I was doing with Nikolai Bobev and other people in Leuven, where we reproduced the second subleading term. Okay, so that's the broad overview of what we're doing.
Next question. There is no n squared.
Yeah, so there is no n squared. It's I don't unfortunately have a good explanation of why there is no n squared. Like maybe it will become clear as we go along. Yeah.
I think there are some theories in which the coefficient in front of n squared is non-zero. It's just the ones that you look at will have that.
Right. So indeed, in other theories, the leading scaling is not n cubed. There are cases where the leading scaling is n squared or even n to the 3/2. And so what's important is that there is a leading and a subleading term, and the precise scalings are theory dependent statements. So I'm just giving you a particular example of this of the ADS-CFT duality where these are the leading scalings. Okay, so what is this particular example? I will be brief here, but essentially what we're considering is a set of M5 branes. The M5 brane has a 6-dimensional world volume, and 2 of these dimensions wrap a Riemann surface with genus G. So I would put hats on the genus. So that's like 2 torus. It has 2 holes. For example, when G is equal to 2. So 2 of the directions of the M5 brane, they wrap this compact manifold, and then there is this Riemann surface lives inside a Calabi-Yau threefold. I will not describe this because it's not the aim of this talk, but what's important is in that this purely UV description, this is what M-theory can tell about the story, is that there are 2 parameters of this geometry, of this internal geometry that matter in our case. The first parameter is G, and the second parameter is a rational number Z, which is related to some Chern numbers of this Calabi-Yau. Okay, so for our purposes, we have just this, the UV physics is described by the number of branes and those 2 parameters. Okay, so for every set of these parameters, one has an incarnation of the ADS-CFT duality. And in particular, the claim is that M-theory on ADS5 cross sigma G cross S4 is equivalent to an n equals 1 superconformal field theory of class S. I'll describe these words in a second. On R cross S3. Okay? So, and again, for every set of G, Z, you have a version of this reality, of this duality. So, give me G and Z, and there would be a particular field theory that can be described, and that particular field theory would be equivalent to M theory on ADS5 times an eternal manifold. So the ADS5 CFT4 in this picture is this ADS5 and this four-dimensional manifold on which the CFT lives. Okay, again, I will not go into detail. I just want to pinpoint the UV parameters that would appear throughout the whole story. And now I will go and describe one by one, first this side of the duality, and then the other side of the duality. Okay, if there are any questions, let me know. Good. So the space on which we put our quantum field theory is R cross S3, where R stands for the time, and these are the spatial coordinates. And actually, I would write down a metric on which we put this theory, because I want to emphasize some features. Okay, so I would have a metric which is essentially well, time, and then the trisphere written in these funny coordinates, and also there is like the time appears fibered on the trisphere in this particular fashion. And the reason I'm writing this is because I want you to notice this constant and this constant, and they will play a role in what follows. But also, in addition to that, I forgot to tell you that this theory has U1R symmetry. And that's very important. It's a super conformal field theory. The U1R symmetry rotates the supercharge, and well, it's present, and we implement its presence by a background gauge field. So this gauge field is not dynamical, its setups are background, and well, in this setup, I would write it as such. Of course, you would come and tell me that I can gauge this away and nothing, so I can just not write it down, but very soon we're gonna go to Euclidean signature and consider this R instead to be a circle, in which case I would not be able to gauge away the background field, so I keep it here. And so here we are, we have these constants, phi, omega 1 and omega 2, and those are considered background, in which we consider the thermal system. Okay, for now we're going to talk about thermal systems. Soon enough we're going to bring the temperature to 0. But okay, so these are the chemical potentials, if you wish, of the system. And in this setup, I can write a partition function as trace over the Hilbert space system. J1, J2, and R are operators in a Hilbert space, and they are related to rotations, to the U1 R symmetry, and the Hamiltonian. And here, this background that we fixed already appears as coefficients in front of these operators. And so this is the usual standard definition of the grand canonical partition function. Okay.
So this is conformal n equal 1.
Yes.
Could you explain more of these coordinates, how they are related to, say, the spherical? Is there any relation to generalized spherical coordinates, or how they appear?
Yeah. So basically, if you set these guys to 0, so we don't fiber the R coordinate, the time coordinate along the S3. This would be the S3 written in some Hopf coordinates, and I don't remember off the top of my mind how to coordinate transform to the usual stereographic coordinates. But there exists a coordinate transformation which brings theta, phi1, and phi2 to the usual stereographic coordinates.
Okay, and then when you include this dt correction, is it still conform to the flat?
Yes. So this is just like redefinitions of. I mean, of course, I can just redefine a new coordinate.
Yeah, but phi's, I suppose these phi's are cyclic coordinates. So
Yes. So the reason why I'm doing this is because the ensemble that I'm considering is that. Well, okay, for that I
So
have
phi is continuous parameter, and you sum it with some parameter with cyclic symmetry.
Yes. So okay. So you're correct to complain. Okay, I probably should have presented this in Euclidean in the first place, where this t would become periodic, and now I would have a periodic coordinate.
But even if you compactify R plus 1, then still this omega should be then discretized, should be somehow quantized in order to also to.
Yeah, so in a way, the discretization comes from the fact that viewed as an operator in this language, it would act on the states of the theory, and each state would pick up a concrete discrete value of omega. Yeah. So okay. So I will actually immediately go to the Euclidean picture, where things hopefully would become more clear. So I make time periodic by weak rotating. So we go t goes to.
But it is even periodic in real time if you consider integral dimension. So in particular in the so-called global conformal invariant theories, the real time is periodic as well.
Okay,
which is equivalent to integrality of
The conformal compactification of Minkowski space is sphere times a circle
even divided
divided by Z2.
Okay. Right.
So you have indeed periodicity in conformal time even in the Minkowski
And then this is the second period, so we have double periodicity in this case.
Yes. Okay, so let me try to let me go to Euclidean signature. I think things will become more clear when I do that. So the reason why we're doing that is because, as we all know, thermal physics in Lorentzian is equivalent to Euclidean physics, where the periodicity of the Euclidean time is the inverse temperature. So this is the whole reason why we're doing this, and this becomes plus d tau. And now here we have minus I d tau, and we have minus I down here as well. And now the thermal ensemble that I'm considering is the following. we have tau phi1, phi2 is identified with tau plus beta and phi1 and phi2. So if you wish, by redefining my phi1 and phi2, I can also make them periodic. In this case, they will be periodic with imaginary pieces in the periodicity. And I have just like written this whole thing in coordinates where this is captured by the metric in which I put the background on. The important piece is right. So yeah, I guess this is the this is the ensemble that we're working on, and these like okay, not constants, but yeah. So these constants here are fixed. They set up the thermal ensemble in which we're working, and right. So that was a little bit of probably overly complicated motivation for me to write this partition function as it is. And so we are now in Euclidean time, and we're considering
Sorry, can I just, before we erase it?
There are two backgrounds actually, quiet parts.
So is the metric that you're writing now complex or not? All the parameters apart from I are real, right?
yes. So the metric that I'm writing now is complex. Okay, so the correct terminology, I think, is that it's complex, but it's still a Hermitian metric, meaning that it is a complex metric, but it is an allowed complex metric in the same sense that a metric of a rotating black hole, if I naively weak rotate time alone, there would be imaginary pieces left in the from dt d5, for example. So in that sense, it is a complex metric, but that's okay. Good. So now the whole point of me doing this is that now finally I want to introduce the supersymmetry algebra that is present in this story. And you have a supercharge that satisfies the following anti-commutation relation. Okay, good. So I would use this relation. And also on this background that I wrote, of course, to preserve supersymmetry, we need to admit a killing spinor that can live on this background, and this would enforce a condition on these fugacities, and the condition is okay. So supersymmetry dictates this relation, this supersymmetry algebra, and then there is another condition on the background on which I'm considering everything. And now I would use these two relations, and I will just plug them in into this formula, and I will rewrite it as such. Okay, so what has happened here is that so this is SUSY algebra. This is Killing spinor exists in the background. And now we have this and this. And in using these expressions, I have rewrote the partition function. I have introduced two like redefinitions of these thermodynamic potentials, which go as okay. So it's like using these relations. It's a one step to get from this partition function to this partition function. And now we actually use the, so let me mention first that before we assumed that beta, omega 1, omega 2, and phi are real. This condition, they can keep being real if I keep this number n to be 0. However, now because of the appearance of this I, they would become complex. And that would be a big part of our story. And I will explain more about this peculiarity in a second. But for now, I just redefined the big omegas in terms of these little omegas because they're more convenient for what we do later on. I will also define another, I will also redefine phi in the following way. It will only appear in a second, but let me write it down now. Okay. So the point of rewriting things as such is that I started off at finite temperature, but I want to bring the temperature to 0, that sending beta to infinity, and I also want to impose supersymmetry, in which case these omegas would go to 1, 1, and 3/2 for the phi. And I want that to happen in such a way that the newly defined fugacities remain finite. So we started off at finite temperature. Now we're going to go to supersymmetry and extremality, simultaneous and extremality, 0 temperature, and we'll see what happens. But okay, so we have this expression here. Turns out that this factor, where this is the R symmetry charge, from the charge assignment of the states in the theory, is for all n, and all, is equal to -1 to the f, where f is the fermion number in the game. And so for people who have like worked with supersymmetric indices before, are starting to see that a structure like a supersymmetric index appears here in this game, and in particular the partition function is then equivalent to, so basically this -1 to the f and this piece here, they combine to give you the super conformal index of the theory. I can explain more if there are questions. For now I just want to write down the general statement. The general statement that the partition function is equal to, and I will try to make this curly, is equivalent to e to the minus some ground state energy of the system, and then the index of the theory, which, so the Hilbert space has a ground state, and then which has some energy, E naught, and this energy is related to what appears here, and then the excited states are bosons and fermions of the same energy, which are paired. So first excited state would be, we have a boson, and then also be a fermion with the same energy. And now this factor of -1 to the f, where f is equal to 1 for bosons and -1 for fermions, would cancel all of these excited states. So this index does not count.
is ground energy in conformal invariant field theory?
In this case, I mean, the supersymmetric Casimir energy. So that would be in the sense that if I write this as beta E naught, where I don't say the word ground state energy, we would be able to write that d beta of log z, something like this.
Can you explain a bit more? So the I is mapped to which thing on the left hand side? I mean, the equality that you make between the traces. What is the definition?
Yes. Okay. So let's. I was trying to be too quick, so I would write down the formula for the index clearly, and I think it will become obvious what's going on. So basically, we have this factor here. This factor I claim is equal to -1 to the f. But then there is also this right here. Now, the index is given by trace, and I will describe a trace of what in a second. But let me just write it down as it is. Now we have this factor with the omega I ji plus r over 2, and we have the factor of -1 to the f. Okay? And so now, because of the -1 to the f, all states, so there are states for which Q acting on them is 0. So these are going to be my ground states. And then there are states for which Q acting on them is not 0. So for all of the ones that it is not 0, this factor here would produce exactly the same value, and the difference would come from f, giving plus or -1. So these guys would cancel. So this object would in fact only count the states which are annihilated by a supercharge. So these are going to be the ground states. And well, because of this, you can see that this object is entirely independent of beta. So I can actually rewrite the index as trace -1 to the f, just e omega 1i ji plus r over 2. If I just agree that I will only count states which are annihilated by Q. So that would be the index. And from the way I presented the story, it appears that, well, okay, I'm just rewriting, so the partition function should be equal to the index. However, I have not been careful in how I treat the ground state, and I don't know exactly how to answer your question, but it is those states in the superconformal field theory which are annihilated by Q, and those states will give a contribution as such, and this contribution is known as supersymmetric Casimir energy. It's some sort of an analogy of the energy of the vacuum, as far as I understand.
Has to do with some conformal analogy, right?
So indeed, so this is the next point, is that these analogies of the ground state would be entirely controlled by symmetries, and in this case by anomalies. So this is the point of this rewriting. So after the whole dust has settled, the partition function is equal to something times an index. The point is that this something can be calculated at large n, because it is controlled by anomalies at large n. In principle, for arbitrary n, that would not be true. But the leading and the subleading scaling of this e to the minus beta node would be controlled by anomalies, and we only have to deal with the index. Also,
I'm sorry, I missed something. There was only one J1 now and not J2.
yeah. So I'm using a notation where omega I and ji, the index I, runs between 1 and 2, so that I don't.
The next term doesn't have I at all.
Um,
Is that Ji plus something? Not dependent on
yes. So I mean that this is written omega 1 J1 plus R2 plus omega 2 J2 plus R2. Just you don't wanna, yeah. So this is the full. It's just a shorthand for this. Yeah.
It's not clear from.
Yes. I apologize. Thanks for the question. Good. So we have this description, and now this we have been talking so far for a generic n equals 1 superconformal field theory in 4 dimensions with a U1 R charge. I have not specified anything else for this theory. I would still not specify anything in the next sentence, but after that we will. So the claim is that if I rewrite my answer as such, so I've just taken the log on both sides. So this f naught is the thing that appears here, and it is the thing that is controlled by anomalies. And this log I is an index that there are ways to calculate it in certain Lagrangian theories. You can calculate it with supersymmetric localization, for example. But again, I want to keep the discussion generic. And remember that we are living on a circle times S3. Now, this object is controlled by anomalies. And now, this is my background. Now, let me consider a scenario in which I make, and now this beta is like meaningless because this is just, as I told you, the answer is independent of beta, so this is just S1 times S3. And now we can make the S1 small compared to the S3. So that would be equivalent to some Cardy-like limit, similarly to 2D CFTs. And in this case, because again beta does not appear, it is more natural to think of this limit as me sending omega 1 and omega 2 to 0, or like making them small.
And this is the same as this one over there, which is the power of -1.
Sorry?
The step over there is the same as those which is in the power of -1 to the, still on.
This is the fermion number.
Yeah. So this f is like this. So this f is a curly f, and this f is equal to plus minus 1 depending on.
That's
yes. Yes. I should be more careful with notation. So thank you for correcting me. If there is this certain limit in which I make S1 small compared to the S3, and in this limit, very similarly to the case of 2D CFTs, in 2D CFTs in the Cardy limit, the partition function picks up like the conformal anomaly. In a very similar fashion, when I take this limit, this guy would also be controlled by anomalies. And so, I'm not presenting this calculation, I'm only giving you the final answer of this analysis, is that this entire object minus log z is equal to then we have trace R, where trace R cubed and trace R are the linear and cubic 't Hooft anomalies of the theory. So the 't Hooft anomalies usually arise as triangle diagrams of a global symmetry, global symmetry, global symmetry, and they make such that some conserved current, which is conserved classically, is no longer conserved in the quantum theory, and these things can be calculated given a theory. We can calculate trace R and trace R cubed, and so this is the final answer. And of course,
Excuse me, I missed where you defined 5, 3.
so phi cubed
Thank you.
was defined similarly to the previous guys. So this is the definition. It's this potential phi which appeared in the background gauge field for like one.
Okay, sorry.
Yeah. And so it's essentially beta, the thing minus its supersymmetric value. Good. So from now on we can forget about big omega 1 and omega 2 and big phi, because the main players in the game will be their small versions, which are appropriate for supersymmetric analysis. Good. So of course I have taken this Carvey limit, which means that there are corrections here, exponentially suppressed corrections of the scale, essentially size S3 over size S1. Okay, so this is the leading term, the subleading term, and then corrections. Good. So now, in field theories, there is a famous relation between 't Hooft anomalies and conformal anomalies. Oops. So this is a generic relation in field theory again.
So A and C should be defined in superconformal theory, yes?
Yes.
What is the definition?
So
Some traces of energy
of
momentum.
so the stress energy tensor would give you.
This is in 4 dimensions. right?
This is in 4 dimensions, so there's 2 of them, as opposed to only C in 2D CFTs. So this is like analogous to the central charge, but there's 2 of them appearing right here. And this is just rewriting the story instead of the 't Hooft anomalies in terms of A and C. Which, the important point for this talk is that A and C can be computed holographically, and that would play an important role for us. For now, I just want to say that this, up until here, it's a generic statement about 4D SCFTs. But indeed, there is a way to calculate trace R cubed and trace R for the particular theories that I wrote down. And the expressions are some complicated function of G and Z times n cubed. Let me call this complicated function, I don't know, like F3, 1 and F3, 2 of G and Z, n, and then some other functions, n. So this means that whenever you see A minus C, it is small compared to, for example, 5A minus 3C. So this goes as n cubed. It also has an n factor of n. Of course, this like large n expansion continues. Okay, but we only care about the leading and the subleading behavior. So indeed, the answer that we expect from the CFT side is something that scales as n cubed and something that scales as n. And in front, we have some functions of these velocities. And depending on the theory, maybe we have some other data which originally came from the compact manifold of the M theory that's in question. But what's more important is in fact these particular functions of phi, omega 1 and omega 2. So we have a prediction from field theory of how the partition function should scale at large n. So now the question is, can we reproduce this prediction in supergravity? Good. So how would we go about this? Maybe I want to keep the final answer.
You can solve it.
I will write down the answer here and keep it up. So field theory is that log z is equal to okay, so this is what we should match. Okay, and I keep it up there to see if we indeed hope it's visible. Okay, yeah, good. So now we go to the gravity side, and I would try to first be schematic in terms of in terms of attempting to compute the path integral of M theory. Of course, I'm not going to compute the path integral of M theory. If I did, that would be great, but I cannot. What I can do, however, is work in supergravity and introduce higher derivative corrections. So the idea is that we start from 11D, but then we go down to ADS 5 cross an internal manifold. And I would consider a theory on this ADS 5. So I would consider a 5D supergravity. Now, because we are in gauge supergravity, there is no scale separation. So the size of this guy is the same as the size of the internal manifold, which means that I would carry KK modes in general, but it would turn out that for our purposes, they would be subleading, more subleading from what we care about, but nevertheless they're there. And now so my 5D theory is usually written as okay. So basically, the point here is that we are working in 5D minimal supergravity with a gauge field, but for now, I'm only writing down the gravitational sector. So there's the Ricci scalar and the scale of ADS and the 5D Newton constant, and I have some matter, and I'm only writing down the bosonic sector. Okay, so this is our theory at two derivative levels. So two derivatives appear here. That's why it's the standard Einstein theory. And good, so this is our starting point. And the path integral, this object that Kirill correctly said that it might not even be well defined, if we can attempt to define it, it would be some sort of a path integral that is, again, not understood very well, but it is this object. So integrate over all fields in the bulk, all fields which have a fixed set of boundary conditions. So this curly phi now, think of curly phi as omega 1, omega 2, and phi from before. So now instead of writing these three guys, I will only write one. So there's a set of boundary conditions that are on the ADS boundary, and I have to fill in the bulk space with fields that have these boundary conditions, and I have to integrate over all of them, and I have to integrate the action of the theory. Next. And now some Lagrangian appear here. But this Lagrangian is not this Lagrangian in general. If I substitute it with a two-derivative Lagrangian, I'm not doing all the quantum corrections in the of n theory. So this Lagrangian, in fact, contains an infinite series of higher derivative corrections. So what I have in this theory is infinite set of KK modes, infinite set of higher derivative corrections, infinite loops because of this, and that's hard. So we work at leading order. At leading order, we consider only this guy as usually, and we approximate this using the saddle point approximation as a sum over saddles. And now here we have some loops where this I alpha is the Euclidean on-shell action of each of these saddles. So this is usually we approximate this integral like this. Right, and now let me make the assumption that there is a dominating saddle, and that the dominating saddle is a black hole in ADS5. So alpha equals 0 is dominant. It is the black hole. Okay, and the answer that you get out of this is that minus log of n of z is given by some function of the fugacities, which are, I remind you, boundary conditions for the bulk fields. And now, well, there's going to be some dimensionless thing here. I have two scales in the problem, and the two scales are L and G5. So a dimensionless quantity that I can construct is L cubed over G5. In 5 dimensions, this works out with dimensions. So this is the expectation from evaluating this guy on this theory. Okay? But now, I can, of course, include higher derivative corrections, and I would start, because we want to have piety, we include 4 derivatives, skipping 3 derivatives. So my corrected Lagrangian, as usual in like just effective field theory in the Wilsonian sense, the first thing that will happen is that these bare couplings G5 and L will get renormalized, and then I would also obtain higher derivative terms such as some coefficient r squared plus other higher derivative terms like Riemann squared, like everything that you can build up from the fields of the theory with some coefficients which, well, as of now are arbitrary. Okay, and so the idea would be that we would use holography to fix these coefficients and know exactly what they are, precisely coming from the brane description, and we will just work, we'll truncate this series at this level, at r squared, like 4 derivatives, and see what happens. So what would happen is that this function, it would become something like this, some other function of the number c. And there might be however many arbitrary couplings I'm allowed to include by symmetry in this theory. So there is a sum over these couplings. To make things dimensionless, I again multiply this by the ADS scale, but this is the expected answer. I will now use the standard law that these corrected couplings get expanded in perturbation theory, and I would replace this with the original couplings that I have, but I would just modify this function. Okay? So this is the expected answer. The expected answer is that I have something that scales as L cubed over G5, and I have this other thing right here. And so the spoiler of the story is that this goes as n cubed, roughly speaking, and this goes as n, and these functions we will be able to fix. So that's the spirit of writing down high derivative corrections in supergravity, fixing their coefficients with holography, calculating these functions, and making sure that these functions are precisely this, and that the L cubed over G5 and L over these coefficients are precisely equivalent to the anomalies from before. So that's the spirit of what's going to happen. And what's the time? Roughly.
Well, precisely 2:15, but it's the time. But you have so much time as well. So.
No, because I.
Not infinite time, of course, but
Yes.
in any case, we started late.
Good. So, yeah, basically, so now we have this general story of what we expect to happen. So now, does this happen in reality? And for this, I would introduce the dominant saddle. So the dominant saddle is this so-called CCLP black hole for Cvetic, Lu, Po, and Chong. Okay, so there are some people that in 2008 wrote down a black hole which is a solution of 5D supergravity whose bosonic action is this thing. Okay, so the action is a rather standard thing. There's a U1 gauge field with field strength F is equal to dA. There's a Chern-Simons term, and then there's the usual gravitational term right here. So this theory turns out to admit a black hole which has charges, which has two rotations. So it's going to be an analog of charged Kerr-Newman, I guess. So it's going to have two rotations, electric charge, and of course energy, like mass. So these are going to be the charges of this black hole. I'm not going to write down the metric of the black hole because it's going to be too long to write down. But it's a fully fledged solution of this theory, and as of now, this solution is not supersymmetric. Okay. So, if you take this black hole, which in Euclidean signature schematically looks like this. There is this is the radial direction. There is an S3 here, and so now when I go to the boundary, I obtain the theory on which that we studied before. And so now there is this cigar geometry that I make from going to Euclidean signature, making sure that there is no weird thing happening here at the tip, would indicate that in Euclidean signature, I have temperature beta. And again, from going to the near horizon metric in Euclidean, you obtain omega 1 and omega 2 angular velocities measured with respect to a non-rotating frame at infinity. And so I have these thermodynamic potentials that appear here, and there is also another thermodynamic potential, phi, which is defined. So these guys, they come from regularity at the tip. And this guy comes from, it's defined in the usual sense of evaluating the gauge field, first contracted with some Killing vector of the geometry, evaluated first at the horizon, and then subtracting this at infinity. And V is a Killing vector made out of d tau or dt, and two directions, which two u1 directions, which are reflected by the presence of these two charges. So this narrative, I just want to mention that there is from the standard black hole thermodynamic picture of Bekenstein and Hawking from the 70s, this black hole has these 4 thermodynamic potentials and these 4 charges. And these objects we can calculate using the standard rules that the great people informed us to use. Good. So I want to rewrite things a little bit so that it's clear what's conjugate to what. So basically, this is how the thermodynamic variables are conjugate to each other, like thermodynamic potentials and charges conjugate to each other. And this Q, the electric charge, would play the role of the U1R symmetry that we discussed before. And everything else has roughly the same interpretation. Good. So again, you can calculate these charges, and also you can just calculate the horizon area. From, again, calculate the horizon area. It's the area of the horizon over 4 g Newton. And you can start. You can check the various thermodynamic properties of the black hole are satisfied. So now I want to go to the limit, to the supersymmetric limit, and this is where this black hole is interesting, because we're used to in flat space to be thinking about the limits to 0 temperature and to supersymmetry as equivalent things. However, in ADS, it turns out that the SUSY limit, it does 2 things. Very similar to the CFT story, it informs us that the existence of a Killing spinor that is regular at the tip of the geometry enforces the very same relation that we had before. Is equal to 2 pi I. So that is, before we had this exact same field theory gives this, and it says that it's equal to 2 pi n, where n is an integer. Gravity says this is equal to 2 pi I and n is equal to 1. I don't have a good explanation why, but for n equals 1, field theory and gravity agree on what is meant by supersymmetry, and also, as before, gravity also gives this relation between the charges, which is exactly the same relation as we get from the dual picture. But when you implement the limit to supersymmetry, these things become true, and you notice how these thermodynamic potentials become complex. And also, this limit to supersymmetry does not immediately bring the temperature to 0. So when we take a limit to supersymmetry, we have this funny situation where we have a black hole with complex thermodynamic potentials. In Lorentzian signature, these black holes has closed time-like curves, so it's pathological. However, in Euclidean signature, everything is fine because, well, time is compact. There is no issue of closed time-like curves. So, and the charges are indeed as well complex. So everything is complex in the Lorentzian picture. In the supersymmetry limit, everything is complex. Okay? But so now we can also take the limit to extremality, which in addition to SUSY, so there is this nomenclature that BPS means SUSY plus extremality. And in this limit, the charges and the entropy become real, while the Euclidean on-shell action and the potentials remain complex. The upshot of this analysis is that, so I would not describe precisely how to calculate the on-shell action. As usual, there is issues from divergence, because, yeah?
How would you describe the black hole in complex coordinates?
So the black hole in complex coordinates is, again, you start from the black hole which has two rotations in Lorentzian, and then you weak rotate time. If you only do that, because there are cross terms between time and an angle, there is an imaginary piece multiplying dt d phi, for example. So now you have this complex metric. What people usually do is they also weak rotate the rotation parameters of the black hole to imaginary values, such that they work on a real Euclidean section. However, in this particular case turns out to not be necessary, and one just works with the complex metric, and the final answer for physically relevant observables, such as the black hole entropy, would be real. At least in this particular case, this is how it works. I think that in general, the procedure should be weak rotate time, weak rotate the rotation parameters, such that you work on a real section in Euclidean and calculate everything there, and then only in the end, weak rotate back the rotation parameters. And so the metric being complex is not the problem here. It's not a problem. It's not the most exciting feature. The most exciting feature is these thermodynamic potentials being complex, because this is what the field theory dictated. And a priori, if you think of the field theory fugacities being related to thermodynamic potentials, and you find complex fugacities, you would be asking, well, what is your supergravity doing? So in this case, we see that in the SUSY limit, indeed, supergravity also dictates complex thermodynamic quantities. But when you go to the BPS limit, where, again, in Lorentzian, also CDC is in Lorentzian. So if you wish this limit to only supersymmetry, from a Lorentzian perspective, is this like a mathematical crutch to be able to allow you to actually go to the BPS limit, where things are real and you have an entropy for a black hole, which is zero temperature and supersymmetric. So it's like an intermediary step, allowing you to essentially take the limit. So basically, this is your geometry. However, when you take beta to infinity, this throat becomes infinitely deep. So you have two divergences. You have a divergence, the usual divergence that you would deal with using holographic renormalization or background subtraction, or however you wish, from r going to infinity. But then there is a divergence of beta going to infinity as the throat gets infinitely deep. So the procedure is to go to supersymmetric case where beta is there. Well, it's complex, but it's not infinite. Express everything nicely, and only then take the limit to zero temperature. And that is indeed possible, and one gets a nice answer for the entropy and the on-shell action. Okay, so let me tell you what this final answer is. Good. So the final answer for the renormalized Euclidean on-shell action, so this is renormalized Euclidean, is 16 over 27 pi L cubed over 8 G Newton, and then phi cubed, omega 1, omega 2. Where omega 1, omega 2, and phi in gravity are defined precisely in the same way that we define them in the field theory. They just have different interpretation. But this is still, for example, phi is still beta big phi minus 1, when big phi is one of those guys that we define in the black hole case. So, sorry, not 1, but 3/2 for this one. Okay, so indeed we are happy because we obtained this much right here. Okay, so now, but does this coefficient match this coefficient? And indeed it does, because from just generically, if you try to compute the conformal anomaly using holography, the answer would be that this particular combination is equal to, let me get it right, to the conformal anomaly A, which is equal at leading order to the conformal anomaly C. Remember, we're in 4 dimensions, there's 2 of them, and at leading order in large N, they're equal. So we have this, and now I also have to give you a relation between the tooth anomalies and the conformal anomalies, which is somewhere here. All right, let me try to get it right. Over 9. Yes, good. So so basically now when A is equal to C, this is this is why I'm missing in the formula that I presented to you. There is a 6 and a 24, and this is like unknowing conventions that different people use, but trust me, in the paper we were actually careful with these coefficients. But essentially the point is that this I can calculate holographically and figure out that it's related to the conformal anomalies, relating the conformal anomalies to the tooth anomalies. Indeed, we get a match for this first term. And we're happy, so now the question is, can we match this term as well? And we can. And the way to match it is inspired by actually work by Kirill on 5D supergravity and what sort of higher derivative terms you can include. So now we switch gears after we have matched the first term, and we include higher derivative corrections. Basically, turns out, okay, new section, HD corrections, which I think is a great name because it sounds like high definition, but it's not. So, good. So, the claim is that in 5D, and you should really ask Kirill about what I'm going to say right now because I might not know everything. In 5D, super conformal, supergravity. So that's the usual supergravity, but with like auxiliary fields turned on. In this theory, there are supersymmetry tells you that there's only 2 higher derivative invariants that you can write, Weil squared and Ricci squared, and they come with some coefficients C1 and C2 that are not fixed so far. And then when you gauge fix to 5D Poincare supergravity, this results in a big Lagrangian that I'm not going to write everything out of this Lagrangian, but well, if it does what I advertised would happen. The bare couplings like G5 and L get renormalized with corrections of C1 and C2, and then the Lagrangian is like essentially is the 2D Lagrangian, the two derivatives. So this is like 4 derivative and 2 derivative Lagrangian with renormalized couplings. And then there is other terms. So, for example, just to give you a feeling of how things look like, the R squared term. Sorry. The R squared term looks something like this. But there's like 14 more terms like this, involving F, various combinations of the curvature tensors and F. And so it's like a big mess, but you write it down and, okay. And now we want to calculate something in this effective theory, in 4 derivatives. And if you follow the precisely same procedure as before, you find that the renormalized on-shell action, and I have to say words before I write this down, and the words I want to say is that turns out that in the 4 derivative theory, if you evaluate it on the corrected, so in principle, you corrected your theory, you should find the dominant saddle in this corrected theory. And it's going to be some version of CCLP where the constant C1 and C2 would appear in it. But it turns out that this is precisely equivalent to the 4 derivative action evaluated on the uncorrected solution up to order C1 squared. And this is a very nice feature, and it comes out through using equations of motion for the 2 derivative theory, and one can view it as a happy coincidence that allows us that simplifies our life in performing this calculation. So here I take the CCLP black hole that we usually have in 5 dimensions, and I just plug it in this action, and I evaluate. And what happens when I do that is that the renormalized Euclidean action is equal to L cubed over G5 minus 16 pi squared. Now we have L C1 plus 6 C2, and that closes the bracket. And we again reproduce what we expect from the leading piece. But then there is also a piece which is 4 pi squared square root 3 LC1, and again omega 1 squared plus omega 2 squared. So just this calculation, the way I write it right now, it looks kind of simple, like nothing. It looks like, of course, yes, of course they match. So basically this term here matches, and this term here matches. But even getting these like functions correctly, remember that I calculate the potentials, for example, in terms of some metric parameters. And in fact, it's if you expand these expressions in terms of the metric parameters, it's like a huge mess of like the metric parameters in the story. So you have to eyeball it and see that indeed this is the combination, or you just know the combination and you check that it works. If I just give you the expression in terms of the metric parameters, it's kind of hard to spot that it amounts to this simple answer in the supersymmetric thing. But it does. And so again, I have this here, this piece, L cubed over G5, which we argued should be leading. And then we have L times these coefficients C1 and C2 which we argued should be sublimic. And indeed, if you take the four derivative theory and you go to the boundary, you can start computing correlation functions in the boundary holographically and match them, because they're essentially allowing you to relate the C1 and C2 to the conformal anomalies. And I will not write down the expressions because it's not that illuminating. C1 and C2 are related in some way in terms of the conformal anomalies. And when you're careful with exactly what's the relation between C1 and C2. So basically C1 and C2, you relate them in some way to the conformal anomalies A and C, which you relate to trace R cubed and trace R, and you match these functions here, and also turns out that you precisely match the coefficients as well. And yes, yeah?
There, at one point on the left now, you started with conformal supergravity, and then you went down to Poincare supergravity.
Yes.
And now, suddenly, conformal stuff like A and C appear back. So there is something that doesn't match here.
Yeah, so what I mean is that I take this supergravity theory and I go, for example, I compute the conformal anomalies of the field theory, but I do it holographically. So I work with Poincare supergravity.
How then you discover conformal?
Well, I mean, at the boundary, for example, of the space-time, the boundary is going to be conformally equivalent to the metric on which I define the field theory, and we calculate these A and C using
I mean, the bulk is only Poincare
Yes.
supergravity, but the boundary is conformal supergravity.
the boundary is conformal field theory.
Okay.
Yes. So these A and C are purely field theory descriptions. Yeah. But we relate them to these both parameters C1 and C2.
Yeah, okay. Passing from
Yeah.
from bulk to boundary. Okay.
Yes. So and that's an important step because you need a way to relate them. And this is actually the crucial input. If you wish, if I only write down the four derivative theory with C1 and C2 and I tell you nothing else, I've actually achieved nothing, because you need to say how are they, like what some UV input needs to tell what's their values. And that UV input, if you wish, comes from holography. It's like a roundabout way. In principle, I should start from 11D, include higher derivative corrections, know exactly what they are from M theory, which I don't know how to do. I should reduce everything, keeping track of how these coefficients C1 and C2 appear. The claim is that if you do that task, which I don't know how to do, but if someone comes along and is able to do it, C1 and C2 will be precisely related to the conformal anomalies of the dual theory in this fashion. And indeed, that's kind of the message of the story, is that holography works not only at leading order in N, but also at subleading order in N. And that's what I had to tell you. And do you have questions?
Yeah, thanks for the talk. And any questions? Well, I do. So, can you tell us a bit more about this renormalization when you have four derivative theories? Did you have to include some additional boundary terms, the holographic
Yeah. So
part of it?
So Kirill is asking about the UV divergences from R going to infinity. So there's two methods to deal with them. Either you do holographic normalization, you include counter terms, or you do the naive silly thing, which is background subtraction. You evaluate the on-shell action of the black hole, and you evaluate the on-shell action of the ADS, and both of these things diverge, but they when you subtract them, you get a finite answer. And these procedures are equivalent up to finite counter terms, which is annoying, but we don't know how to deal with these finite counter terms in four derivative supergravity. I can tell you later about the work by the Padova group who included some counter terms, but of course they also did not include finite counter terms. So there are two procedures to do this, and we know how to get the answer, but of course there are there might be hidden subtleties. But these finite counter terms that you can add, they turn out to be you can sort of get rid of them by anyway. Like I can tell you more about this.
So it's a long story.
It's a long story, but the upshot is that background subtraction, the naive thing, works in this setup, and it's not. Yeah,
So what you did immediately gives you the answer that you expect.
Yeah. So this answer is done background subtraction, black hole minus ADS.
Okay.
Yes.
Other questions?
So there is a picture that you start, you have a boundary.
Yeah.
And there is nothing peculiar there, but when you go in the book, you start to discover black hole, one black hole, many black holes, etc., etc. How many black holes are in your picture?
Yeah. So yeah, good question. So you're asking about. So the prescription tells you that give me boundary conditions, and I have to sit down and find all possible bulk field configurations that smoothly fill in the bulk with those set of prescribed boundary conditions. And here I was working with one such saddle, which I work with the Euclidean saddle of some like 5D black hole with rotate. There are of course more saddles like MKS or like other more exotic things. If you wish, this analysis, the fact that these things match so non-trivially, says that these other saddles, they come as later on terms in N. Of course, there is no proof that this is the case, but it's just considering only this saddle, we are able to match leading and subleading precisely. Everything fixed. There's no freedom anymore. So if there are more saddles, they should be more subleading. And of course, it's a very exciting challenge to find more saddles and see how exactly they're more subleading, and maybe also take the field theory answer and see what happens later on. It's going to be much harder because it's no longer going to be controlled by anomalies. So much more work to do to answer your question.
Well, I can comment a little bit maybe. So in the field theory answer that you give, there is this hidden, one of the variables is too many because it relates to the others, but it relates in a more generic way than in gravity.
Yes.
Because of the n.
Yeah.
So it is not, you do have a match, but only for one of the n's. It might be that you still have dominant saddles that instead correspond to the other values of n.
Aha, okay. Right.
Because this is another question that I think is not yet answered.
It's not answered, no.
What is the why is n arbitrary in field theory and in gravity it's fixed to be 1?
Yeah, so indeed what Kirill is saying that in field theory we have omega 1 plus omega 2 minus is equal to 2 pi I n, and you're saying that the gravitational saddle corresponds to n equals 1, but then there are.
I don't know if there are other saddles.
I think there are some theories in which people consider saddles for different values of n, but in a completely different setup. But
I don't even know if it's different setup. Maybe there are some papers discussing other values of n, but I don't think I can tell you much more than that.
Yeah. Speaking of peculiarities in gravity, I just want to leave you with an idea of something. The charges of the black hole I wrote in supergravity, when you go to the BPS limit, there is some nonlinear relation between them. For example, q squared, q cubed plus j1, j2 squared, whatever. Some constraint between those charges, which comes from supergravity alone. I don't know any reason why in the field theory there should be such a nonlinear relation between the charges. So that's another puzzle.
I think this is related to you, whether you take the limit to supersymmetry or to supersymmetry plus extremality.
In gravity, yes. But if I only know field theory, I have some charges, and why would they be related?
So, but if you relax the extremality part, just
Yeah.
think of Euclidean supergravity. Without extremality, you get rid of this constraint.
Right. But there are indeed puzzles in this story that that are open. Yeah.
Other questions? Oh, let's thank Pascal again.